it's Olivia. Welcome back to your endocrine chapter. In this section, we'll talk about the function of the posterior pituitary. We've already talked about the anterior pituitary. And while our anterior pituitary has 6 hormones that it releases, and those are all produced in the anterior pituitary, our posterior pituitary only really has 2 hormones that it is going to be responsible for releasing. So the first is oxytocin. Oxytocin is made in the hypothalamus, but it is stored in the posterior pituitary. And that's the same for vasopressin. Vasopressin, or antidiuretic hormone, is made by the hypothalamus and then stored and released from the posterior pituitary. So it's great to keep that in mind with both of these hormones. If you ever get a question about where are these hormones produced, the answer is actually hypothalamus, but if they ask you where they're stored, then the answer would be posterior pituitary. Okay, so first, let's talk about vasopressin. What is vasopressin and how is its release controlled? Well, vasopressin's main job is to increase water reabsorption in our collecting duct, so it's increasing water being reabsorbed from our urine, and that is going to leave us with more concentrated urine and allow us to save more water for our blood. So if vasopressin's job is to save more water in our blood, it should make sense to you that it is going to respond when we have very high osmolality, so very concentrated blood. If we have too high concentration of a lot of solutes, or we have electrolyte levels that are much too high, that is going to be one way that we can trigger the response of vasopressin, which is then going to add more aquaporins into the collecting duct. As it adds more aquaporins into your collecting duct, this will increase water reabsorption from our urine, leading to more concentrated urine but more dilute blood, and that will fix our high osmolality problem. Similarly, if we have low volume levels intravascularly, vasopressin will also be released. And if you look down here, you can see that I've included a diagram of your RAS system. Your RAS system is also going to be important for stimulating the release of vasopressin. So to quickly review, your RAS system is controlled by the macula densa cells. So the macula densa cells in your juxtaglomerular apparatus are going to be always sensing the amount of sodium that is passing by them. And when that level gets too low and you're not getting enough perfusion to the kidneys, then your RAS system is going to say, okay, we are intravascularly low and we would like to maintain more pressure to your kidneys, so it is going to turn on. The release of renin will change angiotensinogen from the liver into angiotensin 1. Angiotensin 1 is then going to get converted to angiotensin 2 by ACE in our lungs. And then angiotensin 2 is going to stimulate, amongst other things, the adrenals to release aldosterone, eventually consequentially increasing our blood pressure. So that's a quick review of the RAS system, but why is that important for us? Well, angiotensin 2, in addition to stimulating the release of aldosterone, is also going to stimulate the release of ADH. So angiotensin 2, when the RAS system is turned on, will also stimulate the release of ADH, and that's going to be another mechanism by which our body controls the levels of ADH. So that's antidiuretic hormone. Now let's talk about the other important hormone that is stored in your posterior pituitary, and that is going to be oxytocin. So oxytocin has a couple of different jobs. I always think of oxytocin in relation to breastfeeding as well as childbirth, and its job is going to be the job of milk letdown. So how does this work? Well, if you look over here on your diagram on your right, you can see that we have a baby suckling. When a baby is suckling at the breast, this is going to stimulate the areola. The areola is going to send some signals to the hypothalamus that it is being stimulated. The hypothalamus is then going to be stimulated to release oxytocin. Oxytocin will subsequently travel back to your mammary glands, and there oxytocin is going to trigger your myoepithelial cells to contract. So they're going to contract and they are going to squeeze the milk out of the lactiferous ducts, and that is how you get milk letdown. Now, one important point of clarification here, oxytocin is not responsible for making the milk. That is going to be more of the role of other hormones like prolactin. Prolactin stimulates the creation of milk from our lactotrophs. Oxytocin is more responsible for the milk letdown reflex. So when you have a baby suckling at the breast, when you have stimulation of the areola, it's going to stimulate the release of pre-made milk, but it is not stimulating the creation of milk itself. So just a point of clarification there. The other important job of oxytocin is going to be important for uterine contractions during childbirth. So during childbirth, as the baby descends further into the pelvis, it is going to cause uterine stretch, And this uterine stretch is going to feed back to the hypothalamus, tell the hypothalamus to communicate with your pituitary to increase the release of oxytocin. This oxytocin is going to cause the uterus to contract. We'll get some uterine contractions. This will subsequently increase the uterine stretch as the uterus is contracting against that descending baby. And this uterine stretch will then feed back and increase more oxytocin release. So that is why when we talk about oxytocin, we call this a positive feedback loop. Additionally here, I think this is a very ingenious tie-in that the hormone responsible for uterine contractions that will lead to childbirth is also responsible for the initial milk letdown effect. And I think it's a really beautiful system that we have kind of this built-in 2-for-1, that your body is smart enough to know that you're not going to need your milk letdown until you actually have that child. So the hormone that stimulates the uterine contractions that will start childbirth is also going to stimulate your milk letdown at the exact same time, so that milk then is ready for when the baby requires it. Okay, so we've talked about vasopressin and oxytocin, but how would they ask you about this in a board style question? Well, something they might ask you is something like, a G3P2 woman presents to the hospital in second stage of labor. She rapidly progresses to the third stage and spontaneously delivers a healthy infant. The patient continues to bleed profusely, however, rapidly losing over 3 liters of blood. The medication indicated to stop her bleeding has which of the following additional effects on mammary tissues? So we have a woman who is presenting, she delivers this healthy infant, but then she continues to bleed profusely. To me, that sounds a lot like a postpartum hemorrhage. 3 liters is definitely a postpartum hemorrhage, so she would fit into that category. She has postpartum hemorrhage, and the question asks us about the medication indicated to stop her bleeding. Well, one of the medications that we use to stop postpartum hemorrhage is going to be oxytocin. So oxytocin is one of those medicines, because it causes uterine contractions and causes clamping down of the uterus, can be very helpful for stopping postpartum hemorrhage if a woman is bleeding excessively from her uterus, because by clamping down on that muscle, it can clamp down on some of the vessels as well and cause those to constrict and slow or stop the bleeding. So we're talking about oxytocin in this question. But the question asks you, the medication indicated to stop her bleeding has which of the following additional effects on mammary tissue? And because you watched this video, you know that oxytocin's specific effect on mammary tissue is going to be not milk production, but milk letdown. And that is how you would answer that question. Now, I hope this video was helpful, and I'll see you next time.